All right, so this is a quick walkthrough of the midterm 2 exam you just took. I hope this can help you a little bit in better preparation for the final exam. So let's get started. The first thing is on the front page, please write your name and print it like clearly enough so that we can read it, and print your name as it is showing up on your UCLA ID. Like, don't use nicknames or abbreviations. Okay, let's get started. So for any test taking, the first thing you want to do is browse over the entire exam, read through the instructions, and make sure you know what to expect on the exam, right? How long is the exam? What are the kind of problems to expect? So let's see. On the front page, we say show all your calculations and work. So we get partial credit. You want to show what you're thinking about, so we can give you that partial credit. And then to stop writing when the time is called. Okay, nevertheless, let's get started. First, let's take a quick look on the multiple choices. We have 10 multiple choices, 4 points each. And if we look at it, some of them are easy, and some of them requires assigning of stereo center. So we might as well take a few minutes on it. So in average, we're planning around like 2 to 3 minutes for each multiple choice problem, right? And these are also problems that might need a little bit more time than just look at it and get the answer instantaneously. And then we went into the short answer problems. So these are the problems that you might want to not spend too much time on it. If you're looking at some of these short answer problems and you're like thinking, oh, this is taking too long of my time, you might want to just leave it there and then keep going and come back and finish up later. And let's keep going. At the end, we have 2 big problems. This one is our example did in class like several times, draw stereoisomers and label the relationship between them. Also like doing NMR shift for these molecules. And let's see. We have our comprehensive problem, cyclopentadiene. This is similar to the example we did, which is the furan example we did in class. And acidity, MO, and let's see, is it a chiral molecule, and the challenging problem. So by just going over the exam, you get an idea about how much time I should allocate to each of the problem. Like multiple choice, each should take like no more than 2 minutes. And then the short answer is about 2 minutes, or let's say 3 minutes, because you need to write it down, or even 4 minutes, right? We have 10 of them. So 40, 20, and then you have about 30 minutes left for the big problems. Okay, so let's get started. Multiple choice. The time I start is about 6:05. Let's read it. It says in the UV-vis spectroscopy, what is the transition happening in the UV-vis spectroscopy? So it's UV-vis spectroscopy. So if we go back to our notes, I'm pretending we don't remember what exactly that is. Right, so the note says UV-vis spectroscopy, and let's jump in. Here we talk about energy levels, and that's ground state, excited state, E photon related, and UV-vis absorption have light source, and the absorption takes place. So obviously we're talking about the jump here from a ground state to the excited state, so from your HOMO to the LUMO. So let's go back and write it out. It must be our electronic energy levels. Round 2, assigning stereo configuration and find a molecule that is R. So this one, we can first rule out C. This is achiral. We have 2 acyl groups that are same to each other. And then let's look at A, B, and D. Let's just go one by one. For A, we have 1, 2, 3. So it's clockwise, hydrogen on the vertical. Oh, okay, so we get our hit. Our answer is A. And then keep going. Integration value in an NMR spectrum provides information about what? So it's talking about NMR spectrum. So let's jump back to our NMR spectrum. And here we go. We're talking about integration. So let's go to my lecture note where we talked about integration. Splitting pattern is too far. Okay, integration of the peaks. So it reads integration reveals the relative number of hydrogen nuclei, or the relative number, right? So in this case, we're talking about the ratio between different kind of protons in ethanol. So do we have an answer there? Relative position, so no, that's chemical shift. Number of hydrogen in each type, okay, that sounds right. Splitting pattern, no. Chemical shift, no, so it must be B. And keep going. Homo-LUMO gap. Right, so this one, HOMO, highest occupied molecular orbital. So we can read it. Highest occupied molecular orbital. And LUMO, lowest unoccupied molecular orbital. So A is obviously correct, and we can keep going. Okay, 1 to 5. Which of the following molecules is aromatic? Aromaticity, let's see. What's in aromaticity? Aromaticity, here we go. What are the criteria of aromatic compounds? So when we're talking about criteria of aromatic compound, we have 3 rules, right? You want a closed loop of p atomic orbital. You want it to be a planar molecule, and you want it to follow Huckel's rule, or 4n plus 2 pi electrons. So let's go back and search for these molecules. First molecule, it is planar, and then we have 1, 2, 3, 4, 5, 6. We have 6 pi electrons. So A is right, but it looks a little bit weird. So let's look at B, C, and D and see if we can rule them out. So for molecule B, this is obviously wrong. You have an sp3 carbon in the ring that breaks down that loop of electron. C, that's the same reason. You have an sp3 carbon on there. And for our molecule D, well, boron only have 3 electrons, so it doesn't contribute to your loop of electrons. And this has 4 pi electrons, so it's anti-aromatic. All right, 1 to 6, let's keep going. So in this molecule, this is the example we went over in class, but let's just do that again. So first of all, the conductivity is the same, so we can definitely rule out B. And we can also rule out diastereomers, because it looks like we have a mirror plane in the middle. But what about A and C? Now let's just assume you do not remember, the example we did in class. But here, imagine you're rotating this chemical bond so that you end up having the Newman projection. So what does that mean? So it means if we start by looking at the Newman projection here, let's say I'm looking through this chemical bond here. Let's say on the top, we have, well, our wedge, like a SO group. And then you dream here we have our methyl group. Now in here we have our hydrogen that is dashed. And what about the other group? So on the other carbon here, the ethyl group is on the bottom. And this one, the methyl group is here. And the hydrogen is here. All right, so after drawing this Newman projection, what we have is, you can imagine rotating one of this carbon, either the front one or the back one, by 180 degrees. What we're going to end up having is a Newman projection like this. Right, I'm rotating the bottom one, so I'm keeping the front one the same. I'm rotating it by 180 degrees so that it's eclipsed on top of each other. And this is what I get. Now it becomes really obvious, right? They're all eclipsing over each other, and this molecule must be a methyl compound. That's why this is A. Okay, let's keep going. Fischer projection of the enantiomer of this molecule here. So there are 2 different ways to do it. If you're really familiar with Fischer projection, you can just go ahead and draw it, or you can assign a stereocenter and then find the correct, stereocenters. So let's just do by the hard way. Here we have 1, 2, 3 going this direction. This is a R. And we have 1, 2, 3, Let's go in this direction. This is the R. And on this one, we have 1 on CH2. That's 2, 3. So it's going this direction. So it's counterclockwise. This is S. But it's really, we're trying to find the Fisher projection of the emitter of this molecule. So the molecule we're trying to find is SSR. All right. So let's just look at one of it. You don't have to assign stereochemistry for every single carbon here. Just once you do it, you know what that stereochemistry looks like. So let's get started by this carbon 1. We have 1, 2, 3. So it's going this direction. And then it's hydrogen on the horizontal. So we're flipping it back. So this is a R. So our A is definitely not correct. We want our first stereocenter to be S. So this one looks right? This one is a stereocenter, the mirror image of that. Or if we can assign it, it's 1, 2, 3, clockwise and flipped. So this one is an S. What about the middle one? So let's do that. We have 1, then go here, here, we have chlorine, so 2, 3, so it's going clockwise and flipped. So this one is an S, and that looks promising. Let's keep going. We have OH, this is 1, and top 1, 2, 3, going back and flip. This is R. You don't even have to work on C and D because we already know B is the correct answer. You can always come back and check the stereochemistry of molecule C and D just to make sure. All right, next up, 1 to 8. Which one of the following compound will only show singlet peak? So let's think about it. So first of all, we can draw the mirror plane here, and then these 2 carbons are equivalent, these 2 carbons are equivalent. So this one has 2 neighbors, so it's a triplet. And this one has, well, the triplet here, so it's going to be a quartet. And remember, the chemically equivalent hydrogens do not shield each other. What about B? So B here is actually having only 1 chemically equivalent hydrogen, and it must be a singlet. So B is correct. And what about C? So C here, we have a hydrogen here, and then we have hydrogen here, and here. Here, here. But this is a planar molecule, so these hydrogens are equivalent. Now let's think about these hydrogens. We have this hydrogen, this is equivalent, and these 2 will shield that, creating a splitting pattern. So this will be a triplet. And these two do not shield them because they're equivalent to each other, but this hydrogen will shield it, so there will be a doublet. So C is not correct. Now what about D? D in this case, we have, well, obviously different different symmetry plane to make them equivalent. So we have 2 different kind of hydrogens, right? So these hydrogens are equivalent, and then the CH3 are equivalent. Now, if you think about this molecule, we have these hydrogens do not have any neighbor, CH3 do not have any neighbor, so that's why both B and D are correct. So I give you credit if you put B or D. Now this sort of answers our question here already, right? We have 2 different types of hydrogens that are chemically not equivalent to each other. So this question is asking for exactly 2 peaks in the proton NMR. So it must be D. Again, if you've got the time, you can come back and check why A, B, and C are not correct. And well, let's do that. So in here we have 1, 2, 3. We have 3 different types of hydrogen. For B, we have 1, 2, 3. Still 3 types of hydrogen. For C, we have 1, 2, 3, 4. So we have 4 different types of hydrogen. Okay. Now 1 to 10. In NMR spectroscopy, what does a downfield shift refer to? So now let's think about what is downfield shift. Let's see if we do not remember. So this one is 0 ppm, or where your TMS is. That's your internal reference. So downfield means we're going down. Right, so we're going away from the reference compound. So this is definitely not correct. To a lower chemical shift value, which is not correct because right, our reference is 0. more shielded proton NMR. So if you remember what that TMS looks like, right? You have silicon in the middle, and then CH3, 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 CH3. So all these CH3s are equivalent to each other, and they shield each other very strongly. So not correct. So, well, D is our only correct answer. How's my timing? I'm at 6:17. All right, so we spent about 12 minutes on the multiple choice. We're doing okay on the timing, so let's just keep coming back. And keep in mind, we have some problems we might want to come back and revisit. Like, for example, this one, you can check the C and D later on. And for some of the problems like here, 1, 2, you can check the B and D later on as well. But let's just keep going. Problem 2.1, draw the Fisher projection of trios. So again, this you have two different ways to do it. If you're good with Fisher projection, you can just draw it directly. If you're less confident drawing the Fisher projection, you can always assign the stereochemistry of these two chiral center and then do it the harder way. Even if we're doing it the harder way, right? OH is my 1, and then 2, 3. So this one, we're going counterclockwise. This one is a S. What about on the right? We have 1. Now here we have a carbonyl that's double bonded, so it has 2, 3. So we're going backwards, clockwise. So that's at R. So if we put it, the CH2OH on the top, so that's this group here. And then we have 2 chiral center, and on the bottom we have the carbonyl group. What's the relative position of the OH? Now, again, if you're less confident drawing it, you can always draw it and just check whether or not you get it correct. So this is our blue stereocenter. So let's say 1, 2, 3. So we're going this way, it's clockwise, but hydrogen on the horizontal. So we flip it. This must be a S, and we're happy. And what about the bottom? Let's see. Let me just put it in the same way, and let's check it. We have 1, 2, 3. Let's go this way. It's S, but it should be R. So that means my OH and hydrogen is flipped. So let me just redo it. We have 1, 2, 3. Going that way, and the hydrogen on the horizontal. Flip it. Now that is R. So this is the question. If you put the carbonyl group on the top and the alcohol on the bottom, it's the same. Just keep it consistent. All right, 2-2. Now let's read the question. In the UV spectrum of beta carotene, the maximum absorption was obtained at lambda max equals to 453. Estimate the homo-lumo gap of beta carotene and use the provided color wheel to predict the color. Okay, first predict the color because that's easy enough. We're talking about 453, and actually my color wheel is a little bit weird. So both red and orange are correct. I mean, this one is wrong, but this one is wrong, but both of them are correct if you like. So it's going to be red or orange, and the reason it's red or orange is this molecule absorbs green or blue light, so it shows up as the orange or red color. Now estimate the homo-lumo gap. What does that mean? So if we think about what is happening in the UV spectrum, and by the way, this actually gives you the answer to problem number 1 here. What is happening is we're measuring the energy gap between your HOMO and LUMO, right? So if we have occupied like this, and then we have H mu of energy, and we're getting excited after the light is being absorbed. So naturally, we know that delta E equals to H mu equals to HC over lambda max, and plug in the numbers. Have Planck constant, speed of light. Well, we're representing it in kilocal per mole, so we need a Avogadro number here. divided by lambda max, which is 453 nanometer, or 453 times 10 to the negative 9 meter. You plug in the number to the calculator and get 264 kilojoule per mole. Can translate that into calorie, about 63.1 kilocalorie per mole. Most of you are able to get this problem correct, which is good. Okay, let's keep going. What we have here? Simple cyclopentadienol, and it's given the molecular structure here. So it's telling you the cyclopentadienol is a highly unstable organic compound. Provide a short explanation for this observation. So this is the point of view, like you need to be familiar with the concept we were talking about. This is a demonstration, like you can't just learn a concept during the exam. There are two different concepts we learned that can potentially introduce instability into a molecule. One is steric repulsion, and two is anti-aromaticity. So this molecule for sure does not have steric repulsion. Even if I add in all the hydrogens, they're like really far away with each other. They're pointing away from each other. So no steric repulsion. It must be anti-aromaticity. So what is the criteria of anti-aromaticity? Let's see. We have a planar molecule, and all my carbons on my planar molecule are sp2 hybridized, and we have a total of 4 pi electrons. So this is anti-aromatic. And, well, does it explain why the molecule is unstable? Well, anti-aromatic is telling you the molecule is unstable. All right, let's keep going. Borazine. Borazine, well, molecular structure shown below is a remarkably stable boron compound. Can you provide a short explanation for this observation? Well, this looks like an extraordinary molecule, and how can we explain why it is stable? So, talking about stability, so we have two different ways to think about it. Whether you have like resonance stabilization, or you can talk about it using aromaticity. Actually, both of them are valid, like depending on how you argue for it. But if you're using resonance stability, you need to draw out that resonance structure, which in this case, before in the neutral form, that's what your molecule looks like. Right, and you need to push the electrons around. So here we have double bonded, double bonded, double bonded. But this, well, resonance structure, it will get you partial credit, but it doesn't really explain why this molecule is so stable. And again, you have so many partial charges built up. How do we say it is more stable? And the real reason here is we're looking at a cyclic molecule. Now, after you draw this resonance structure, you'll be figuring out, oh, this looks really like my benzene. It's a 6-member ring. We have 6 pi electron. It is planar. So this is an aromatic compound. You see, like, you don't have to write an essay here to rationalize what you have in your mind. Just think it through and write down the necessary information only. Okay, that's it. Now, let's look at these two molecules. Label the following molecule as aromatic, anti-aromatic, or non-aromatic. Well, let's just count the number of pi electrons and assuming these are all planar molecules. Let's look at it. We have 1, 2, 3, 4, and in the example we did in class, we know that sulfur, like furan, have 2 lone pairs, and one of them would contribute. So we have a total of 10 pi electrons. So molecule A is aromatic. What about molecule B here? So this one, again, is very obvious. We have a sp3 hybridized carbon, so this must be non-aromatic. All right, let's move on. 2 to 6. Below is the proton NMR spectrum and the molecular structure of PHF, tetrahydrofuran. The peak integral is about 1 to 1. Assign the peaks to the corresponding hydrogen nuclei in PHF. Explain your assignment in 15 words or less. Let's look at this molecule. This molecule obviously have an internal plan of symmetry. So we have two different types of hydrogen, if I write them out. One are these hydrogens that are closer to oxygen, and two are these hydrogens that are more away from the oxygen. So both of them are triplets, and this is consistent with our setup here, right? You have two different kind of hydrogen that's about 1 to 1 ratio. Now the only difference is by their chemical shift. So it's been a while. If we don't remember chemical shift, what are the factors contributing to chemical shift? We can always come back to our lecture note and double check on it. This is aromaticity, that's the wrong note. Let's see. Okay, here we go. Chemical shifts. You have two different factors affecting the chemical shift. One is, well, tertiary versus secondary versus primary, but this is not applicable. Both of them are secondary. And what about here? Okay, so we have electronegativity. The closer your CH group is binded to the electronegative atom, it is more downfield, or it's less shielded or de-shielded. So let's go back to our exam. So our part B is more de-shielded. So let's see. We can just simply draw arrows here. And you can say these are de-shielded by electronegative oxygen atom. And again, it's within 15 words or fewer. You don't have to write a whole essay for this kind of explanation. How many words I use? 1, 2, 3, 4. And that's good enough. Okay, next up. Given the molecular structure of 3-phenolthiophene, draw in and circle all hydrogens that will appear as a doublet in the proton NMR spectrum. How many doublet peaks do you expect? Right, so when we're talking about doublets, we're talking about hydrogen that has only one neighbor. So this hydrogen here doesn't have any neighbor, so it's going to be a singlet. This one here has a neighbor right here. So these two are valid, and I should draw them in. And this one doesn't have any hydrogen. This hydrogen here has one neighbor, so I should draw it in. This hydrogen here has one neighbor, so I should draw it in. And these hydrogen will have two neighbors. This hydrogen has two neighbors. This hydrogen has two neighbors, so they are all triplet, and I don't have to draw it in. How many doublet peaks do you expect? Let's see. Well, we're talking about how many doublet peaks. So are these hydrogen atoms chemically equivalent? These two are not. It's on a double bond. They have different binding environment. But these two are. So we have free rotation over the single bond here. So in total, we only have 3 doublet peaks. Right, so it's 1, 2, and these two are equivalent to each other. Okay, let's keep going. 2 to 8. Identify the stereochemical relationship between the following pair of structures. So let's see. These are Newman projections, and remember we're talking about Newman projections. These you can have free rotation over that single bond, and of course you can do it in the harder way in assigning stereochemistry and see whether or not they change. But for Newman projection, you always have a better way to do it. So if we look at the front, right? So OH is here, OH is here, CH3, CH3, hydrogen, hydrogen. So the difference between the front is just rotation of sigma bonds, which is the same stereochemistry. And if we look at the back, we're flipping the position of hydrogen and bromine. So our stereochemistry of the back is flipped. So they are diastereomers. All right, so let's keep going here. 2 to 9, draw the HOMO and LUMO of 1,3 butadiene. Label all node plans to get full credit. HOMO and LUMO of 1,3 butadiene. It's been a while. Let's check that up. Allylic bond and conjugated diene. So conjugated diene is in this lecture notes. Let's keep going. All right, so that's where you have, right? So that's your HOMO. That's your LUMO. HOMO, you have a node plan between C2 and C3. LUMO, you have a node plan between C1 and C4. So let's go back and draw it. So, HOMO. You have a node plan in the middle, and then you draw the orbitals and shade it accordingly. And then LUMO. And you have node plan like this. And then we draw in the orbitals accordingly. Alright, and that's good enough. Like, don't draw everything else on it. That's irrelevant. Only show the relevant information. Next up, challenging problem. So this one I already put it into small parts on our Canvas assignment. And let's just work on that together. The most hydrocarbons are nonpolar. Interestingly, the following hydrocarbon has a relatively big dipole moment. Draw the dipolar resonance or zeta-ionic resonance and briefly explain why the charge-separated resonance structure is favored. So this question is asking for the dipolar or zeta-ionic resonance structure. If you do not remember what dipolar or zeta-ionic resonance is, it also tells you it's a charge-separated resonance structure. So when we say charge-separated, it means on my molecule, we have a positive charge, we have a negative charge somewhere. So it looks like the middle one is likely to break down into, well, a positive charge or a negative charge. So you can imagine drawing the resonance in multiple different ways. See, 1, 2, 3. So let's say if my 5-member ring has a positive and my 7-member ring has a negative, will the structure be favored? Well, here is anti-aromatic, here's anti-aromatic, so this is not stable. And what about the other way to break down? We have a 5-member ring and a 7-member ring. And let's say we break down, so we have a positive charge on the 7-member ring, negative charge on here. Well, now on both of them, we have 6 pi electrons. So they're aromatic. And they are stable. All right, so that's our 210. What's our timing now? We are 6:35. Let's see, how much time do we have left? We started at 6:05, and we're like 30 minutes ago. 30 minutes passed. Okay, so we have plenty of time. Now let's move on to the comprehensive problems. Now this one, given the structure of this dipeptide L-proline, L-valine, answer the following questions. Draw all stereoisomers of this molecule. For this one, you have 2 different ways to draw it. Either you can draw it via that mirror plane, or you can just draw it by changing the stereo center. So I'm just doing it one way. Both of them are correct, by the way. And this one used to be a wedge, so let me just make it a dash. All right, and then we have stereoisomer C. Let's see, just changing one of it. O and H. Oh, this one must be dashed. Running out of space. All right, and then here, these 2 are mirror image to each other, so I must flip. All right, so these are how we draw it. Now between A and B, these are enantiomers. C and D are enantiomers. Everything else are diastereomers. So let's put it in. A and B enantiomers, C, D, AC, Okay, so that's the end of this question here. And let's keep going. Okay, NMR. Considering the proton NMR for this dipeptide, answer the following questions. No explanation needed, no partial credit. Put your answer in the box. So that's our box. Okay, so in order to answer this question more easily, I might want to redraw my molecule. So let me just see. Find membrane. From here, NH, and then the emit, and then the isopropyl, and then the wedged out carboxylic acid. All right, so I'm just redrawing this. Now the question asks, how many total proton NMR peaks would you expect? So this question, lots of you get it wrong. So if we think about it, first of all, OH, NH, and these NH will all be different signals. In here, we have one hydrogen. That's going to be different. In here, we have one hydrogen. We have 5. These CH3s are equivalent. So 1, 2, 3, 4, 5, 6 for this. In this one, we have a hydrogen that's dashed. 1, 2, 3, 4, 5, 6, 7. Okay, and then these 3 CH2 groups are most people get it wrong. So this is a ring structure. So depending on whether or not these hydrogens are wedged or dashed, they see different things. So first of all, these 3 are inequivalent to each other because of connectivity. And if the hydrogen is dashed in, it sees that dashed in hydrogen. But if it's wedged out, it sees this wedged out NH. So the reason they're inequivalent is because it's the ring structure, we do not have free rotation, and they see different chemical groups. So in total, we have 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 proton NMR peaks. About this one, how many singlet peak do you expect? So when we're talking about singlet, we're looking for hydrogens that does not have any neighbor. So, well, excluding OH and NH. So everything has neighbors to it, isn't it? This one has 2, this one has 3, 4. Well, that doesn't count, so it's 0. And, well, keep going. How many doublets do you expect? Doublet has only one neighbor, so this one has only one neighbor. This one has more than, we have CH3 here. These CH3 only have one neighbor. These 2, now we have 2. Keep going. Well, the hydrogen here, the NH, nope. This one has, well, definitely more than 1, definitely more than 1, definitely more than 1. So we have 2. And these are these hydrogens here. What is the splitting pattern of the largest peak, the peak with the largest integration? Well, the peak with largest integration is definitely these CH3s, like a 1:6 ratio. And what about the splitting pattern of these CH3 hydrogens? Well, it will have one neighbor, so it must be a doublet. And what's the splitting pattern of the most shielded peak? And remember, we talked about primary CH3s or primary alkyl groups being more shielded. So it's talking about the same group. All right. So primary is more shielded than secondary than tertiary. Okay, how are we doing on timing? We are at 6:42. And let's keep going. Comprehensive problem number 2, cyclopentadiene. It has interesting chemical properties. The pKa of cyclopentadiene is measured to be 16, which is unusually acidic for a hydrocarbon. Now it asks you to draw the structure of its conjugate base by deprotonation of its most acidic hydrogen. If applicable, use resonance to show the localization of charge among various carbons and briefly explain the origin of high acidity of cyclopentadiene. So this is a question, typical question. When we're talking about acidity, you should instantaneously link acidity with stability of conjugate base. Right, so if you're going to remember anything in this class, please remember acidity. More acidic, more stable conjugate base leads to more acidic molecule. So now this is the similar example we did. You have 3 different ways you can deprotonate the hydrogen. Right, let's just draw in all the hydrogen. Now, these hydrogens, if you deprotonate it, you will form an anion charge on here, and that anion can delocalize over the ring because before this carbon is sp3, but after deprotonation, it becomes sp2. In comparison, if you deprotonate any of these hydrogen, you would end up with a negative charge on the alkene that cannot further delocalize. So obviously, let's just first write out the dissociation of the most acidic hydrogen, which gives you the structure of the conjugate base. And is this enough? Obviously not. So you want to use resonance to show delocalization of the charge among various carbon and briefly explain the origin of high acidity. So let's do this. And again, we're explaining the origin of high acidity, so we're trying to say why this molecule is so stable, right? Why this conjugate base is stable. So let's draw it out. So now there are several different ways to do it. I mean, depending on if you want to show the arrow pushing or not. I'm showing it just to demonstrating to you like how it's being done. But according to our new rubric, even if you do not show the arrow pushing, that's correct as well. So let's move this way, and we got it here. And then we can move it again. And do the resonance. Let's see. Here. And let's move that again. See, 1, 2. Move it one last time. And all right, so we have a total of 5 resonance structures stabilizing this conjugate base. Now the reason here is this molecule, or any of these resonance, you have 6 pi electrons, and it's a planar molecule, so it is aromatic. And aromaticity brings stable conjugate base. And make this more acidic. So for this exam, you also get credit if you're just saying it's more acidic because of the resonance delocalization. But the reality of this molecule being super acidic is because of the aromaticity. Okay, keep going. 42. Draw the complete pi correlation diagram of cyclopentadiene cation. get full credit, draw and organize the molecular orbitals based on their energy levels and assign the electrons accordingly. So the molecular skeleton and node planes are provided. It's asking for a pi correlation diagram. Let's see, if I don't remember how to do it, maybe I should go back and check what's been done in class. What's aromaticity? It's probably at the end of the benzene lecture, which is obviously aromatic. And let's see. Okay, so here's benzene. Right, so this is a pi correlation diagram we are referring to. First of all, you have to define the energy as our axis and draw the molecular orbital. Whenever you have a node plane, you change the sign and then assign the electrons into different molecular orbitals. So whenever you have the same number of nodes, these MOs are degenerate in energy. Okay, that's how we do it. So let's go back and do that problem together. So first of all, draw the energy level. And let's see, this one has 0 nodes, this one has 1 node, 2 nodes, 1 node, 2 nodes. So the orientation of my MO is 0 nodes, 1 node that's going in between, 1 node that is going through bonds, and on the top we have 2 nodes, one through atom, one through bond. The drawing is a little bit ugly, but that's okay. And there. Right? And these are my skeletons organized according to their energy levels or the number of nodes. Okay, let's put in the energy level as well. These two are degenerate. These two are degenerate. And putting the orbitals, so 1, 2, this one has all the same shading. We do not have any nodes. Here we have, these two are the same. We need the nodes, we switch it. These are the same. We need the nodes, we switch it. This one we switch. And switch. Likewise, like this, switch. Switch. All right, so that's just drawing the MO. And let's read it again. We'll put the electrons in. Oh, it's a cyclopentadiene cation, right? So we have only 4 electrons. Put in electron 1, 2, and then degenerate. They went in degenerate or singly occupied. All right, so that's our 42. Let's keep going. Now, moving on, they say cyclopentadiene undergoes Diels-Alder reaction with ethane to form nobornene. Interesting. The 3D geometry of nobornene is given below. We have the front view, we have the top view. And it's asking, is it a chiral molecule? Well, this top view is actually very obvious. You have a mirror plane that goes right in between here. And now when you're having an internal mirror plane, what it means it is not a chiral molecule, or it is achiral. And the reason it is achiral is because we have internal mirror plane, or if you say internal symmetry plane, making this compound a methyl compound. Right? So that's our 40th string. Keep going, the challenging problem. Identify one pair of chemically equivalent hydrogens in nobornene, then predict how many peaks would you expect in the proton NMR of nobornene. So this is the diagram we provided. This is actually easier if we look at that top-down view before. So now let's look at this molecule. We have this internal mirror plane. So everything that's around that mirror plane, these are equivalent, right? You have that mirror plane, so these are equivalent. But these two hydrogens are right on the mirror plane, and they see different things. Let's say this one sees this double bond. And this one here, okay, let me use a different color, sees a all saturated carbon. So we have a total of 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 different peaks. And well, these are equivalent. These are equivalent. These are equivalent. These are equivalent. But everything on the top, these two on the top, they are not. Right, so we totally see 6 peaks together. And I mean, as long as you have at least one pair circled, you get a partial credit. How are we doing on the time? We're at like 6:52. Right, so overall, I think I'm taking, okay, 47 minutes. And that's including going back and forth on the notes. And now, again, now everything else, like the 43 minutes are the time left. You can check up your answer. So here's a quick walkthrough. I hope this is helpful for you in preparing for your final exam.